Yeah. Welcome, everybody. It's my pleasure to invite you all for the talk today, and our speaker will be Nika Salia. Nika obtained his PhD in Budapest. Erwin Dzieri was his supervisor, and later he was working at Alfred Renyi Institute of Mathematics in Budapest, in Institute of Basic Science in South Korea, then King Fahd University in Saudi Arabia, and since 4 weeks he's working here at Jagiellonian University. So it's our pleasure to listen to his research. Thank you.
Thank you. Thank you. Dzień dobry. Thank you very much for coming and giving me this opportunity to introduce myself and my research here. Today I will be talking about one of the projects which started in South Korea at IBS, and we solved the problem later. So, the title of my talk today is Saturation, number for uniform bow tie. This is joint work with Stein, Hamish. So, as I mentioned, we started working on this project at IBS, South Korea, and while we both hated our lives there, we could not solve this problem there, so this was solved much later when we both quit our jobs. Anyhow, so I will give you a little bit longer introduction for some of you. Maybe this would be too trivial, but very soon we start investigating some interesting problems. So, I'm an extremal combinatorialist, and we love this function. This is Turán number. Or extremal number. What is this? This is maximum number of edges in n vertex graph with no copy of f as a subgraph, not necessarily induced. Not necessarily induced. So, if you have been on extremal graph theory talks, you have seen what I'm going to write here. Maybe it's boring, but this is an example, and I guess example should be one of the easiest thing, and I am going to show you the easiest. So, this is theorem of Mantel from 07, which states that EX and triangle. What is triangle? The interpretation of triangle can be a cycle on 3 vertices, on complete graph on 3 vertices. But it is important that in this case, triangle is a complete graph, because questions when we forbid cycles are generally hard. Is what? This is n squared over 4. And okay, of course, if you are extreme combinatorialist, you remember this number. But if you are not, I would generally give you an advice that I myself don't remember the numbers here. For me, more important are constructions. The first thing is that when I see any kind of this result, I'm asking when this is happening, and is that unique, and so on. So this is achieved by a graph which is complete balanced bipartite graph, where we have color class sizes and half floor and the ceiling. Obviously, there is not only just a triangle, but it is any odd cycle free. Okay, so what does this construction tell me about this number? When we look at this construction, we know that number of edges here is n squared over 4 floor, and there is no triangle, right? By this construction only, we know that the extremal number of n vertices triangle free is at least n squared over 4 floor. While for the upper bound, we need some ideas. And there are many ideas, and for example, theoretically there can be a very nice course, short course, in introduction of extremal combinatorics, where you just take this theorem and you prove it in many different ways. So one of the ideas is they take an edge, u and v, and you know what? Every vertex is either joined to one or to the other one. It cannot be to both. So, and if you check in the construction, for every edge you take, every other vertex is either joined to one or to the other. So, by applying induction, the construction tells you that calculations should work very well. This is one way of proving. The other way is called Zykov symmetrization. Instead of taking u and v, which are adjacent, you take u and v, which are not adjacent. And what do? You would look at them and say that, oh, I prefer u because of degree is at least as large as v. So let's change v. Remove v and add the copy of u. If it was a triangle free, it's still triangle free because they are not adjacent. They're u prime and u. And the number of edges either did not change or increase. So by doing this, you are only increasing the number of edges. At the end, you will get this. Okay. So this was a very quick overview of kind of an idea how we are speaking about these numbers. But once more, just don't forget, we are speaking about saturation number and not an extremal number. But for me and for the people like me, this is the motivation how we end up there. So now we want to generalize this. This is too easy, right? So why don't we study that my interpretation of the triangle can be a cycle or the complete graph. Let's say that, okay, this is complete graph, and then we have an K, what letter I'm using? KR. This is Turán theorem from 1941, which states that this number equals to Turán number nr, which is at most 1 minus 1 over r minus 1, n squared over 2. This is n squared over 2, this is not n choose 2. And what is the Turán number? This is, this is Turán graph. This is a Turán number. So we have r. So as you see before, when r was 3, you took two classes of almost the same size. Now we have r, you take first class, second class, third class, and number of the classes will be r minus 1, and each of them will have number of vertices n divided on r minus 1, either the floor or the ceiling, depending on the period. And then this is an independent set, this is also an independent set, and you take all edges. So, does it matter what is this number? No, I really never remember this. I just remember this, and from here you count that number. So, this is the idea. And then comes, of course, there is many things coming, but firstly, what I want to say that this Turán theorem is counted as the beginning of the extremal combinatorics era. That's when we started studying this function. Of course, before we had Mantle's theorem, even before we knew that the maximum number of edges in the planar graph is something by order 3n minus 6, and so on. Of course, we may count them as extremal results, but this is the really beginning of the era. Even though even Erdős has determined an extremal number of C4s before that, after the Mantel. Okay. Now, fundamental theory of extremal combinatorics. What is this? This is Erdős-Simonovich theorem, which states that Ex and F equals to 1 minus 1 over chromatic number of F minus 1 n squared over 2 plus small o n squared. And what is this number? This number looks like that number. So it is something like Exn. So this says that the only chromatic number matters. And it is one way is trivial. If you know the chromatic number, you know that the Turán graph is free. So you have a construction. Then you need to prove the upper bound. But does it solve all of the problems? Or something, there is a problem in this theorem. So, obviously there are many different tastes. There is the taste when you want to study order. What is the degree of n of the leading term? Then asymptotics, determine the constant. Then determine the next best, and so on. Exact result. Then study the structure, and so on. But mainly we would like to find asymptotics. Like this is the first thing. When we find an asymptotics, we count the problem solved. Sometimes the question is about the order too. Of course, order comes before the asymptotic. So here, it says that if chromatic number of F is greater than 2, then we not only know order, we also know asymptotics and the constant in before n squared. But if n chromatic number of F is exactly 2, is bipartite, this says that the extremal number is small o n squared and nothing else. And it says that problems when F is bipartite are interesting. And we studied that. For example, extremal number of nf is, and cycle length 2L is not known when L is not equal to 2, 4, 2, 3, and 5, right? Okay. So this is an introduction of extremal numbers. Now I want to smoothly go to the saturation. So what do? We are people who likes the problems, extremal problems, which says that we either maximize or minimize some parameters. So What was Ex and F? This was, I gonna rewrite whatever was written, I guess, here. Maximum number of edges in an n vertex graph, which is F3. And I'm gonna add a sentence which was not written there and which was not necessary, and we will see that we need it. And plus any edge makes copy of F. So what does it mean? That if it's maximum, we start adding an edges, and yeah, if we can add an edge, then number of edges are increasing. So when we write here maximum, that comes for free. But if I would say minimum, and I don't require adding an edge makes a copy of F, then you take no edges and you say that everything is alright. So saturation number. So this is exactly the same function, but instead of minimum, we are asking the maximum number of edges in an n-vertex graph, minimum number of edges in an n-vertex graph, which is F3, and adding any edge makes copy of F. Okay, now you look at this and tell me that, okay, Nika, before, when there was maximum, you did not write this sentence. Now I look at this and I don't really need to have F3ness necessary. Like maybe I can remove it. Is it gonna be same or not? I don't know. So let me call it some other name. I forgot what we call it. Set, right? Set, yes. This is semi-saturation. This is saturation. This is semi-saturation. And F, minimum number of edges in an n-vertex graph. I don't ask F3ness, plus any edge, makes copy. Now I would say makes new copy of F. Are they same? Not? I don't know. We will see.
So by you mean that this edge is used?
Used, yes. Exactly. So, just to be on the safe side, very soon I'm gonna start writing case here. So everything here, what we are doing, is for the graph. But don't forget that my talk is about hypergraph. So at some point I will just switch. Okay, now on we are studying for hypergraphs. But yeah, like motivation should be easy. We are speaking about the graphs. And let me give you an example. So you remember Turán theorem for the complete graph. The first thing we would want to find a similar theorem. As I said, that was the beginning. So let's start with the beginning. What is the saturation number of the triangle? What is the saturation number of complete graph on 4 vertices and so on? Theory. Erdős, Heine, and Moore. This is from 1964, I guess. Maybe 9. I think it's 4. So 2 is at least T, at most N. And so let's say K. Saturation and KK equals to K minus 2 N minus K minus 2 plus k minus 2, choose 2. Okay, now you can tell me that I have a bad taste, that I'm writing an important number in a small way and you don't see it. Maybe this was deliberate because once more I say that numbers don't matter. The question is, what is the construction? And okay, for the people who sees the number, I think it is easy to guess the construction. This is, you take complete graph on k minus 2 vertices. This is k minus 2, choose 2. And then you have k minus 2 times the rest of them. So you take a complete bipartite graph in between. And this is independence. So first of all, what is the largest click in here? Largest click, is it size k minus 2? No, it's k minus 1, right? Because you can take all of the vertices here and one of the vertex here. So this is k minus 1. Once more, you cannot have two vertices from here because it's an independent set. You have one vertex here, k minus 2 here. It's k minus 1 is here. Is it f3? Yes, it is f3. If we add an edge, where is that edge? That edge will be here. Does this edge make a copy of a click? Yes, you take all the vertices upstairs, plus these two vertices, and that's the click. And what is this? This construction tells me that this number is either at most or at least. So since we are searching that minimum, so the answer is either this one or less. So now, if the construction before was giving you lower bound because it was the maximum, now it gives you an upper bound. So answer is either that much or the less, but the theorem says that this is optimal. But what is the big difference now? If you see that it is something like nk, and their answer was n squared. So it's linear. Next question, when is it linear? Theorem from Tusa from 1986. Saturation number NF is at most linear. Not always linear, but it is at most linear. I think it's a good thought for the coffee to check when it is not linear, when it is sublinear. Okay, now we start examples. Do we have any questions? Because now I'm gonna dare and I'm gonna ask you some questions and expect you to answer. So, as I said, we extremal combinatorialists like this function a lot. Not because it started, but it has lots of good properties. What is the property? For example, exn1f and exn2f. If n1 is greater or equal to n2, then this will be greater or equal to that, right? Trivial. Why? Because if you have a construction here, the same construction with isolated vertices will work here. So that will be a lower bound. Sorry guys, yeah, I forgot when I mentioned the saturation and saturation, I said that are they equal, but we don't know the answer here, but yeah, both are visible. So one of them is a trivial lower bound, right? So once more, both of them says the same. One of them requires that it should be free, and the other one not. Yeah.
F is always connected?
No. And that is a very nice question.
You don't have problems with
Okay, isolated vertices. So, yeah, we ask these questions generally when n is large. So I got your questions. When n in order to break this inequality, you need to have here n smaller than f. Size of f. Yeah. Good observation. But generally, that was a funny question. There is very big. There is still an open problem. Erdos and Simonovic, which had a trivial counterexample by taking f disconnected, and nobody was. Oh, we all thought that f was connected. So yeah, it was fun. That's a really cool question. Anyhow, here, which way is trivial? So once more, remember the construction is an upper bound. So construction which is good here is good here also, because this has an extra requirement. So construction here is good construction there. Maybe another construction is better. Better means less. So we have trivial inequality. So yeah, I'm not gonna change this. Assume that n1 is big than the size of f. Now, another question. We agree on this. I'm going to remove. Now here we have n, and here we have still n. But I change here, we have f1 and I have f2. And I know that f1 contains f2. f1 contains f2. So here construction is f2 free. f1 contains f2. So if it's f2 free, then it is f1 free also, right? So this construction is good for that. So number of edges is either that many or more. So it is monotone as the function of n, as the function of f. That's why I love it. And that's why I don't like this. And that's why I don't really work on the saturation problems. That's true. Okay, now. Okay, I'm too much in a hurry. I already solved that saturation number fails to have these properties. But yeah, this is what we are going to do now. Saturation number of 2k minus 1 p4 and saturation number 2k p4. Well, let's think about it. What is this number? We have an even number of vertices, and what is forbidden? This is path on 4 vertices. Obviously, like if you have 2 isolated vertices, then you would join them, and that will be an isolated edge, and it would not help. So we don't have many isolated vertices. We might have one, but let's assume that we don't have an isolated vertex at all. Then what is the best thing to have? Edge. Right? This is the proportional the minimum number of edges per vertex. So if we will take lots of edges, that's why I said it's even, because I can take edges. Then, as soon as you add an edge or add an edge, you get the P4. So this number is K. Almost we proved it. But as soon as you have an odd number of vertices, now you cannot take this construction, because if you add an edge, you create a cherry path of length 2, which is not good. So we need to change something, and we take a triangle at the end. So how many edges is here? The number of edges is k minus 1 plus 3, which is k plus 2. Wait. No. K, not plus 3, right? Plus 2. And this is k plus 1, which is less number of vertices, more number of vertices, but the saturation number is decreasing. And this is happening. So it is not monotone as the function of L. Is it monotone as the function of F? So what is the problem in the statement? What might break the monotonicity? The freeness, that it is free. So it can be one free and not the other, and that will break. So this is the only thing it can break. So my construction, F1 and F2, should be that, one of the saturations should be copies of the other one, smaller one. Yeah, okay, so what is this? And what was this? This is this number, right? So remember, this is 4. So you have 2 vertices here, and this is what? This equals to 2 times n minus 2 plus 1, which is 2n minus 4. Yeah. And I want to show that this is strictly greater than saturation number n vertices, and I will write triangle plus an isolated vertex times n vertex. What is this? Let me draw it here. It's a K4 with a pendant edge. So now we are desaturated. And once more, I said that the only way to break the inequality here to use this. So construction of this must include lots of K4s, and yes, indeed, it contains this. So if we take in copies of that, then as soon as you add an edge, at the end, if you have small, whatever that is a click, you need to add edge between, and if you add an edge between, then you have that. So now we prove that this number does not equal. This is less or equal to that number, which is roughly speaking n over 4 times 6, so 3 halves n. And this is 2n. So we have strict inequality here because of the construction contains lots of K4s. Okay? By the way, because of that reasoning, here we have equality because we must have the clicks. Not roughly speaking. So you can actually prove the equality here, but we don't care. So it's not monotone in any sense. Now, question. Is it that inequality, saturation and semi-saturation equal, or sometimes the semi-saturation can be very, very small? So today, in my results, I'm going to show you a very nice example, but a small baby example is here, so if you will not like it, I share your opinion, but I promise that we will see a better. I mean, I'm just saying that this is very artificial and small, And yeah, so saturation, so set 5p4, so n equals to 5, so this is why I don't like it, is strictly less than saturation of 5p4. Why? Because, once more, if it breaks, then construction should contain p4. Take p4 and the edge. So as soon as you, is it 5? Yes. If you add an edge, where is this edge? If this edge is containing this vertex, then you go the direction which is longer. This is new p4. If you add this edge, still you have p4. If you add this edge, then you have the p4. So just check it, that is thing. So this equals to 3. Why not less? Because you need to have at least 3 edges, right? Maybe. If you don't want to have lots of isolated vertices. So that's easy that it is 3. And this is not 3, because we cannot do that. So this equals to 4, and this is the construction, and it's easy to prove. Okay? Now let me try to, actually, I just don't want to spend lots of time in cleaning, even though this is the most important thing I will mention today. So, the topic is bow tie. Bow tie is one of the simplest graph, maybe cherry, let's call it cherry, you can think of. But motivation of this work is much harder, and this was the motivation. I don't remember when was this archive paper, so it was published in 23. This is theorem of English, Ostochka, and Zilli. They put a paper on archive, and they proved that the saturation number of hypergraphs, 3 uniform hypergraph, n vertices, and the graph is C33. This is linear cycle of length 3. So you have this object. Okay? You don't have this, and as soon as you add the hyperedge of size 3, you make this object is at most 3/2 n plus lower order term, and this is 4/3 n plus lower order term. So 4/3, 3/2. It's like 30-page paper. Obviously, I can do better, right? This was what I was thinking. Like it was at least 20, I guess, like 5 years ago. Obviously, I could not do anything. And yeah, reading that paper is also hard for me. It's a nice paper, recommending. And the construction is also nice. I'm not gonna show you the construction, but I will show you a small construction which has nothing to do with this number. If n equals to 9, if you take 9 vertices and all these hyperedges and all these hyperedges, this is all like this. I think so, yeah. This is not containing that, and as soon as you add a new hyperedge, you make a triangle. This is a nice baby example, which makes, for me, the problem interesting. And yeah, I was working on this, no results. But when you start some new topic, you start thinking some baby problems just to learn how things are working. So this is how it started. So, questions about saturation of one hyperedge is trivial. So, we were interested about like what happens for this or for this. This was the beginning when I was starting warming up. Okay, for that, let me write. So first of all, let me say BK is K uniform bow tie. What is this? That B2 is a cherry. B3 is two hyperedges sharing a vertex. B4 is two hyperedges of size 4 sharing a vertex, and so on. Okay? Now, what is saturation number n vertex B2, which is n over 2 floor? Where is this achieved from? This is by taking independent edges. If it's not, if you have one more vertex left, you are leaving it here. As soon as you add an edge, you create B2. And half easy. Saturation equals to semi-saturation also. Good. Now, let's start to work on that, right? This is the goal because we are warming up for the triangle. So here, still the situation is saturation and semi-saturation of n B3, now 3 uniform. B3 is still n over 3 floor plus 3 plus 0, 3 or 2 depending then if 3 divides n, if 3 divides n, 3 divides n, plus 3 is n minus 1 and this is n minus 2. So this says that more or less the construction is take a triangle, hyperedge, 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 and hyperedge if it's divisible by n. If not, then the last component is either K4, 3 uniform hypergraph on 4 vertices, or it is 2 vertices upstairs, 3 vertices downstairs, and you take all hyperedges which contains this. Is it? Yeah. So, and yeah, it's easy to prove it. But what is the main idea? Why this construction works? This construction works because of as soon as you add a hyperedge, it should have at least one vertex in one component. So 3 cannot be divided by 2 plus 2 or 2 plus 3. So there will be a component where your new hyperedge has exactly one vertex. So, and that will make your cherry or a bow tie. So this was when I realized that, hey, wait, okay, this is it. What about this question? Saturation or semi-saturation and P4. This should be trivial. And I don't know many experts, but I know some of them. So I approached them, I asked them questions. Do you know this? How to do it? It's trivial, like it sounds like a baby problem. Maybe it is, and we don't know how to solve it well. This is today's talk. So anyhow, we spent lots of time without any improvements. So, and this was all the time I was in South Korea. This was we had a huge whiteboard, and it was always up, and we had the constructions for n equals to 7, 8, 9, and then we got stuck. No computer was working, and so on. So, yeah, this was the motivation. Now, let me tell you, this was the way I found this problem. But the fact that I found it, it does not mean that it is interesting. So what is other more motivation? So Erdős, Füredi, and Tuza has determined the saturation number of these hypergraphs. What are those hypergraphs? We have K uniform, number of vertices, this is number of vertices, and this is number of hyperedges. It's easy to see that they are unique. For example, we have two hyperedges and number of vertices is 2k minus 2. So they share exactly two vertices. So the problem which I want to study is hk when k is at least 4, two hyperedges, and how many vertices? 2k minus 1. So our problem fits this way of studying. And at the same time, what was known, there was conjecture, which is already solved, of Erdős and Sós from 1975, which says that if n is large, maximum number of hyperedges in K uniform hypergraph without pk, so now maximum number of hyperedges in n vertex K uniform bk3 is, so once more, we forbid two hyperedges sharing one vertex, we want to take more. What do we take? You fix your favored two vertices and you take all of the hyperedges. So it is, what is it? N minus 2, choose k minus 2. So for that, we need to have k at least 4. Obviously, k is at least 4. And this was settled by Frankel in 77 for large n, and by Kivas, Mubai, and Wilson in 2006 for k equals to 4 and all n. So this was done. So I think this explains that the way I got stuck is natural, and maybe that is interesting problem, and yeah, let's try to solve it. So now I'm gonna go into the main results. If you have any questions, please ask. Meanwhile, I will have a break and clean the board.
Is it known that saturation number and semi-saturation number are different when n is large?
Is there an example for that?
Yeah.
For before. So for we will see.
Because here the example was for n equals 5. So
No, that's what I'm saying. That this is that. I know you will not like the example. Please wait. You remember? Yeah, I knew that you would ask that question. Yeah. So. And by the way, that example can be also generalized, as I know. somebody said once during the talk, and people were more expert than me, they agreed with each other. So I did not follow, but I think this taking a path, longer path, and that construct, you take longer path and big N, it should work. But I'm not sure. But yeah, I have an answer on that. Yes. So, first of all, what is our approach? I want to find some numbers. So, do I know order? Do I know asymptotics before I want to? Once more, I want to find a construction. Construction is like, once more, I'm a zookeeper. And in my zoo, there are constructions. This is how I see myself, really. So, but before I do that, do I know at least an order? So, set K and BK and set K and BK are linear. Why are they at least linear? Because you cannot have many isolated vertices, because if you have K isolated vertices, you should there a hyperedge and there is no. And why is it at most linear? Now I'm gonna make a mistake, and are you gonna believe me or not? Take lots of copies of K to K minus 2. Why to K minus 2? Because of if you have two hyperedges sharing a vertex, you have two K minus 1 vertices. So here you cannot have the object. You take many copies of this K unit. Right? You take copies of that. There is no bow tie, but as soon as you add, there is. But this does not prove that this is linear. What is wrong? Yeah, it seems like you have the same taste as me. This proves for infinitely many n that that is linear, but not for every n. So this is not enough. You can have 2k minus 3k, and you can take combinations of this, and for every n you will have. So now these two constructions says that for every n, this is linear. Okay. So once more, this highlights that look, we like extremal number, not saturation number, because of if you know this and you know this, we can assume that we know everything in the middle. Not here. That's why we need both. Okay. So theorem. Campi and myself. K is at least 4. 2n over k plus big O1 is at most saturation k n bk, and this is at most 2n over k plus big O1. So we have some bounds on k uniform semi-saturation now, and we will have a better for 4 also. Yeah. Okay, so let me see the following thing. Now I'm gonna shoot you with lots of theorems. Then I will look at the time and then I decide which bounds I'm gonna prove. So this is another theorem. So this is the same authors, and is at least 100. Saturation number for uniform n before is at least 6 over 13n minus 11 over 13. And why do we write it so precisely? Because if n is congruent to 4, modulo 13 it is sharp. So we more or less determined. You want? Okay, great. So for 4 we have 16 over 13. And let me not forget, at the end you will, oh, okay, we are, I said that I'm not, I am, and I would call this a main theorem. Of Cambium myself, this says that the saturation number n before equals to n minus 3. And this is this. So this is n choose 4 when n is at most 6. This is n when n equals to 7 or 8. And n is at least 9. It's n minus 3. So we proved this. Okay, so 1 hour passed. So I will assume I have 15 minutes more or less left, and we will see. We will finish it in 10 to 20 minutes. First interesting case is n equals to 7. Okay? Yeah, but we did not have n equals to 7. We knew what? We knew the following thing, that if you take K for 3 with 3 isolated vertices, this is the right? If you have several copies of complete graph on 5 vertices, 4 uniform, and 3 isolated vertices, then as soon as you add a hyperedge of size 4, you must have a, no, something is wrong, right? 3 plus 3 is 6. Okay, let me not waste now time on that. We had something, does not matter, and we never had the 7. And then we found the construction for the 7, which is a funnel plane. What is the funnel plane? This is for me, funnel plane is not 4 uniform hypergraph, that's a 3 uniform hypergraph on 1, 2, 3, 7 vertices. N equals to 7. But it's not 4 uniform. How can I make it 4 uniform? So then let's take a complement. What do I mean complement? If in the funnel plane you have this triple, in the complement take this quadruple. And yeah, I will not spend the time now to explain that this is B for free and not only free, also B for saturated. And how many hyperedges are there? the number of hyperedges is also 7. And that's why we have it here, n equals to 7. So then we found a construction for 8 and 9. And finally, we found the following construction, and this construction works for n equals to 10 or n equals to 12. Let's start with a hyperedge of size 4. And we are going to go on both sides symmetrical. This was a generalization of n equals to 10 rule. So firstly, we found it for n equals to 10. We take 3 vertices. I don't want this color. Let me take 1, 2, and 3. And we take 3 vertices here also. And we take this hyperedge, and we take this hyperedge. So any 2 from here and this 2. We do the same there. We take these 3. And this is 10 vertices. There is no bow tie because any 2 hyperedges either they don't meet or they share exactly 2 vertices. And as soon as you add a hyperedge, you create a bow tie. But as you see, this is construction for n equals to 10. How do we generalize it? If the number of vertices at least 2 more or any more, you can take any number of vertices here. But if you take something, it should be at least 2. Either don't take anything or at least 2. That's why there is a jump. Similarly here. And then you take, I want to write. These 3 and this one. These 3 and this one. So what happens? Number of vertices are increasing by 1. Number of hyperedges increases by 1. So if it was n minus 3 for n equal to 10, then it will be always n minus 3. And this was the construction which we found after we found the proof, because the proof told us to do so. Okay, so we have seen the construction for n equals to 10 and 12. For 7, what about for 8? Let me show you for 8 also. N equals to 8, this was, we take 7, 8, 5, 6, 1, 2, 3, 4. And we take all of the hyperedges which contain 5 and 6. And 2 from here. And so on. And this gives a construction for 8, which is n. And this is also saturated. Maybe now the time does not give us the opportunity to really study those constructions and show that they are saturated, but I think, yeah, if you look at those, it will be easy to understand why they are saturated. That they are free, it is easy, because every time you add a hyperedge, it intersects everything in at least 1. So these are constructions. Maybe very briefly I can tell you how we prove this. So, as many proofs in extremal hypergraph theory, we like to take skeletons. What is the skeleton of the hypergraph? There is no definition. It's something like tree in a graph, but it's also not a tree. So we started to construct our hypergraph H, which is B4 saturated, by what? Take a hyperedge and try to extend it as much as you want, greedily. In the way that the hypergraph which is drawn, it should be always connected. So firstly, we assume that H is connected. We are searching for the connected, and then if it's not connected, then you study that. So if it's connected, you start from the hyperedge, and you want to extend as much as you want. Firstly, you know that you cannot do such an extension because this will be a bow tie. So next hyperedge, which I'm going to add with the new vertices, must at least intersect in 2, and so on. So I will take these hyperedges, which gives me 2 new vertex and 2 new vertex, and so on. And as soon as they are out, then I will continue adding hyperedges, which contains 3 existing and 1 new. And once I'm getting n vertices, I stop. So this we would call the skeleton. Actually, I don't remember. Yeah, skeleton, greedy skeleton. And then we showed that no matter in which order, no matter when and where you start taking a hyperedge, and you just are allowed to add another hyperedge which shares 2 vertices with an existing one, there is only one way of getting such a maximal skeleton. Every such maximal skeleton will be the same. Even more, if you do this argument separately somewhere, and I do somewhere, and then we stop, the third person can come and connect these 2 things together. So what does it mean? That this greedy 2 skeleton is not only unique, but it contains any subskeleton. And they are the problem, and that's why we need to speak how they look like, and we need to describe them. In this case, the picture without this hyperedges was a greedy 2 skeleton almost. Yeah, which was the structure, and this is how we found this construction. Okay, so this is a very, very vague idea of the proof here. Now, let me go back and check which proof I can give you in restricted time. So, lower bound, upper bound. Maybe the most general. So, we did it for form. So, I'm not gonna speak about that one then. And I'm gonna attempt to prove that. So, since I already showed you lots of constructions, I will start with the proof. So, K times, okay, H, K uniform, hypergraph, which is P, K saturated. Degree sum V of H, dV. So, what is this? This equals to K times number of hyperedges. This is the thing I want to bound. Okay. So one thing is the following. I'm gonna write this, and then we will discuss. So this is, we are bounding. So I claim that more or less every degree should be at least 2. So then we write 2 times V of H, which is n. But you say that, Nika, no, not really. It is possible that some vertices have degree 1. Okay, let me say that, okay, more or less, a hyperedge cannot have more than 2 degree 1 vertices, because if it's more than 2, I can take 2 here, 2 here, 2 here, and if there is somewhere more, then I will take 3, and that will be a hyperedge which I'm gonna add, and it will not make new copy, or yeah, we are speaking new copy of PK. So this means that maybe many hyperedges have 2 degree 1, but not more. If k is odd, then everybody can have 2, and this argument will fail. So I'm gonna write 2 v of h. So every hyperedge can have 2 degree 1. At most, some negligible number, which very I will bound it by k squared, but it is much less. This is negligible, so doesn't matter. Except the k hyperedges, which each at most contains k vertices. So except this many vertices, everything else has degree 2, except 2 vertices in each of the hyperedge. This is very generous bound. So we bring this there and divide, and we get that E of h is at least 2 over k plus 2 v of h minus. And this is the proof. Okay, what about the upper bound? So, okay, let me do the following. Yeah, 1 hour and 15 minutes is past. So, let me say that I finished my talk here. Thank you very much. And if there is any questions from you, I'll be very happy to give you constructions either for this or for that. So, or both of them if there will be the question. I'm ready for that or any other question. Thank you very much.
Let's thank you.